Hello everyone, in this video we are going to discuss about the mass limit of neutron stars. So what are neutron stars? Apart from black holes, neutron stars are the densest stellar objects formed after the collapse of the core of a supergiant star. Now we are going to discuss about the formation of neutron stars. When the star reaches the end of its main sequence lifetime, it enters into a massive red giant phase, which contracts under gravity until a dense core is formed with electron cloud around it. If the mass of the star is less than 1.46 solar mass and electron pressure successfully withstand the collapse, we get a white dwarf. However, if the star's mass exceeds this limit, the contraction continues until the electrons get pushed into the nucleus. This reacts with the protons to form neutrons and release neutrino. At this stage, we have a perfect neutron core. If the neutron degeneracy pressure can successfully withstand the collapse, we reach an equilibrium. So finally we get the neutron star. So now we will attempt to find the mass limit of neutron stars.
We start with Fermi statistics, where the occupation number for momentum P is given by 1 upon e to the power beta epsilon P, which is the energy associated with the momentum P, minus the chemical potential mu, plus 1, beta here being 1 over kBT, T being the temperature of the system. To find degenerate pressure, we need to assume T goes to 0, which means beta tends to infinity, and in this limit the occupation number comes as a step function, which is 1 for all momentum states less than equal to Fermi momentum and 0 otherwise. Now the degeneracy of neutrons is taken as 2 for spin up and spin down, and we use the standard formula for the total number of particles to get our final expression of Fermi momentum as h cut multiplied by 3 pi square n to the power 1/3, where n is our number density. Next, we calculate the internal energy of the fermions, assuming relativistic speeds, and integrating over phase space and momentum space, we get the internal energy U as some constants multiplied by volume multiplied by an integrand. Now using standard thermodynamic results at T equal to 0 limit, we get the neutron degeneracy pressure P as minus del U del V. This gets us the pressure as a complicated equation of Kf along with various constants, but we will use a much simpler version of this. We will assume ultra relativistic limit where Kf is much greater than 1, and following a few approximations, we will have the final expression of the pressure as h cut c divided by 12 pi square multiplied by 3 pi square n whole to the power 4 by 3. Now we know that the density is basically the number density multiplied by the mass of a neutron, which gets us the equation of state as P equals to K multiplied by rho to the power 4/3, where K is a known constant. At this stage, we compare this to our polytropic equation of state, which is P equals to some constant multiplied by rho to the power 1 plus 1 by n, which gives us the value of n as 3, and we set the density rho as some central density, which we take as nuclear density multiplied by theta cube, and the radial distance r as some known constant alpha multiplied by a dimensionless variable xi. Assuming flat spacetime, from our hydrostatic equilibrium equation, we get the second order Lane-Emden equation as 1 over xi square d d xi of xi square d theta d xi plus theta cube equals to 0, with the initial conditions, that is the value of theta at 0 is 1 and the value of theta prime at 0 is 0. Plotting theta versus xi gives us the first 0 at xi1, which comes as 6.877. Now I calculate the mass limit, which is equal to integration 0 to xi1 4 pi alpha cube rho c xi square theta cube d xi, where the total radius is capital R, which is equal to alpha xi1, and the condition that theta of xi1 is 0. From here, we get the total mass as some constant multiplied by a factor, the value of which we can get by solving the Lane-Emden equation. From the solution of the Lane-Emden equation, we get the value of the factor as around 2.0167, and putting it with the constant, we get the mass limit of a neutron star to be around 5.698 solar mass. Now the radius is related as 14 multiplied by mass divided by 1.4 solar mass to the power minus 1 by 3, which gives us the radius limit of a neutron star to be around 8.77 kilometers.
If the mass limit exceeded the value which we have calculated, further collapse will surely occur, and thus we will reach a singularity, and therefore there will be a formation of black hole. Our calculation do not include several factors such as the bending of spacetime around neutron star because of its very high density, and thus general relativistic effects cannot be ignored. Also, we have neutron-neutron and sigma-omega meson interaction within the star. We can obtain the mass limit, which is around 5 solar mass units, by using Tolman-Oppenheimer-Volkoff equation. Considering particle interaction give us further improved upper bounds. The mass of the most massive neutron star was recorded around 2.35 solar mass unit in 2022. We infer actual data about neutron stars from the merger of binary systems and the released gravitational waves. In 2017, LIGO detected a gravitational wave signal which is around 100 seconds long from such a system. We finally present the references which we have used and the group members' input. Thank you.